Okay, welcome to lecture. And we're going to start up on chapter 14, it looks like. And again, these notes should be up there on Canvas if you need them, but chapter 14 is where we should be at. Looks like most of you typed here in the chat box. So again, if you haven't done so, please do so. So we'll use that as attendance. All right, so last time we finished up talking, grab something here. We finished up talking about chapter 13 and equilibrium, Le Chatelier's principle, and all that good stuff. So we're now going to move on to chapter 14, which is acid and bases. So we're going to cover sort of basic acid and base type chemistry, things like pH, pOH, Kw. We'll also get into how to calculate the pH of strong acids along with strong bases, and also weak acids and weak bases, what to do with those. And we'll finish up sort of talking about salts and hydrolysis type reactions, what happens when, again, salts sort of get made as a process of the reaction between an acid and base, and also talk about diprotic acids as well. All right. Again, if you do have questions along the way, feel free to type them into the chat box, and obviously we'll get those questions answered for you. And off we go, I suppose. Yes. So let's just talk a little bit about acids and bases and some of the basics of them. An acid has, excuse me, an acid has a sour taste. For example, vinegar owes a lot of its sort of taste there to acetic acid. Citric acid, for example, in fruits. They react with certain metals to produce hydrogen gas in reactions you probably are familiar with. So, for example, single type replacement reactions. So if we took some zinc metal plus some hydrochloric acid, again, it will do a single replacement reaction where the zinc would come in and kick out the hydrogen, and we'll get some zinc chloride plus some H2 that's being generated. That's a gas. A little 2 over there, I think, as well. And this is, again, a single replacement reaction, the generation there of hydrogen gas. Pretty much when you do kick out hydrogen there from an acid in a single replacement reaction, you typically will produce, obviously, hydrogen gas. And if you've seen it, it's like bubbles and so forth as you do this type of reaction. Get everybody in here, I think. Hopefully, there you go. They also react with carbonates, for example, and bicarbonates to produce other gases like carbon dioxide. And you're also hopefully familiar with that reaction as well. So again, if you took something like HCl and some sodium carbonate, again, this would be more of a double displacement reaction where the two positive guys basically switch partners. And you'll get some sodium chloride and some carbonic acid. And again, I would do a little balancing here. I'll just go through it. This carbonic acid that's produced quickly breaks down into water and CO2 gas. And that's sort of the plop, plop, fizz, fizz that you sort of see when you react, an acid with a carbonate. It's that generation of CO2 gas. So it's really sort of as you probably learned in 1A there, it's a double displacement reaction followed by a decomposition reaction of carbonic acid, which produces that CO2 and water. Now, bases, on the other hand, they are bitter taste. Obviously, you shouldn't taste any acid or bases. A lot of soaps are basic, so things like Drano, drain cleaner, soaps, those type of things, they're more in the basic type range. When we talk about basic, a word is oftentimes used which is known as alkaline. And alkaline means basic. And you could probably imagine, as you also probably know, hopefully, that a majority of a lot of strong bases, for example, come from group 1 or group 2 of the periodic table. And if you remember, group 1 is the alkali metals, and group 2 is the alkaline earth metals, and thus a lot of bases are sort of generated from there. Things like sodium oxide with some water makes some sodium hydroxide, some potassium hydroxide, calcium hydroxide, and so forth. Now, sort of a early sort of definition of an acid and base was one done by Arrhenius, who did a lot of work with electrolytes. And he basically said that an acid is a substance that has the ability to produce H plus or H3O plus in solution. So here we have hydrochloric acid within some water producing H3O plus, which again is your basic definition of an acid. Really important in acid-base chemistry is the idea that H plus, which is sometimes referred to as a proton, and if you remember, a hydrogen has a proton and an electron, no neutrons. So in order for it to become H plus, it needs to lose that electron, which leaves it just a proton. So H plus and H3O plus are essentially the same deal. So H plus and H3O plus are essentially interchangeable in acid-base chemistry. H3O plus is the hydronium ion, so that is a polyatomic ion, and we use pretty much H plus and H3O plus interchangeably, both in formulas and also chemical reactions. So we'll see both of those guys used. I personally will use H plus most of the time, so I really won't use H3O plus all that much. So almost anywhere I sort of use H plus, you could substitute H3O plus and it'll be the same thing. So just to sort of illustrate, sort of what's the major difference and why perhaps you get H plus or you get H3O plus. So for example, this reaction that we see up here, this is really just hydrochloric acid, which is a strong acid, breaking apart in water. And if you actually include water in the actual equation like they did here, that's really where you will generate your H3O plus from. Now, you could write this exact same reaction another way where you don't include the water, which is very commonly done. So if you just take hydrochloric acid, for example, give it a try here and see if it works. And you basically just break it apart into H plus and Cl minus. This equation and this equation here are essentially the same thing. They both represent really the same thing. That's the hydrochloric acid that's basically in a solution where it breaks apart into H plus and Cl minus. So if you want to include the water, you can. The only real difference in most cases is you will generate H3O plus on the other side. Or for an acid, like I said, it's very common that people don't include the water in the equation, especially when the acid, again, is technically not reacting with anything. It just went for a swim, basically. We usually will sort of eliminate the water aspect of it, and thus we'll also eliminate the H3O plus part. So the H plus, H3O plus, basically the exact same deal. And again, I personally will probably most of the time just write an equation like what we just did there, up like this one up on top, where we just break it apart. Now, an Arrhenius base is something that produces hydroxide in solution. So a lot of bases, a lot of strong bases actually have OH in the actual formula itself. But there are some that does not have OH in the actual formula, and NH3 is actually a weak base, which we'll talk about a little bit later on as well. And NH3 is a weak base. It doesn't have hydroxide in the actual formula, but it's able to produce hydroxide like we see over here. So because it's able to produce hydroxide, it is obviously still considered a base. So a very important concept as you sort of go through acid and bases, and something we'll talk about a lot, and it'll be important as we continue on, is the idea of, am I dealing with something that's an acid or am I dealing with something that's a base? And pretty much the simplest way or the easiest way you could kind of determine if that solution, is sort of acidic, or you should be doing things sort of the acidic approach in terms of calculations, or a basic sort of approach, is by looking on the product side. And if on the product side you see H plus or you see H3O plus, then you're probably dealing with some type of acid. If you look on the product side, you see OH minus, then you're dealing with some type of base in that particular case. So that's sort of the easiest way to sort of approach it. Going to be really important to sort of understand that as we start talking about weak acids, weak bases, and hydrolysis, so that you do use sort of the right numbers in your calculations as you continue on. And this was a pretty good beginning to a definition of acid and bases, but a more generic sort of definition came about with Brønsted and Lowry. And Brønsted and Lowry's definition of an acid and base is usually the one most of us sort of think about when we think about an acid and base. And a Brønsted-Lowry is, as it says up here, a proton donor. And again, a proton is H plus. So H plus is what we're talking about here, not just H, but the plus comes along with it. So Brønsted-Lowry acid will donate an H plus, give it away, while a Brønsted-Lowry base will accept an H plus. So when we talk about Brønsted-Lowry, we're talking about the H plus and either the accepting or the donating of that H plus as to whether or not something is an acid or a base. So in this particular example here, where we have ammonia and water, water in this case is acting as the acid, is going to donate that H plus over. When it donates that H plus over to NH3, that NH3 becomes NH4 plus. And sort of a consequence of the Brønsted-Lowry definition is we actually create partners on both sides of the arrow, and we create partners that are related to each other. So with the NH3 being the base over here, it is related to the other side, which is known as the conjugate acid. And when water donates that H plus over to the reactant side, what's going to happen to water is it's going to become OH minus as it loses that H plus. So when we do lose the H, again, the important part is the plus part. When we lose the plus, we become more negative, right? One more negative. So we become OH minus. And that's what we see here. And that also gives us two things that are related to each other. We have our acid on the left-hand side and our conjugate base on the right-hand side. And these two things are related to each other. And there's an important relationship that we see between these two things. And that is, it is a difference of only one H plus. So as we go from the base to the conjugate acid, it's one more H plus. And as we go from the acid to the base, it is one less H plus. And that's really important in order for it to be considered a conjugate acid base pair, which is what these guys are. The only difference that you can have there, the only difference is one H plus, and only one H plus at a time. So if you have more than one H plus difference, then they are not related to each other. The other important thing is on the left-hand side of the arrow where our reactants are, that is typically where we find our acid and our base. And on the right-hand side of the arrow is where we find our conjugate acid and our conjugate bases. So again, conjugate acid and bases found on the product side. Regular acid and bases found on the reactant side. Any questions on that? So again, only difference between those two, one H plus and one H plus only. And again, these are what we refer to as conjugate acid base pairs. So our conjugate acid base pairs. Now, water is interesting. It could actually react with itself. So in one case, one water would be the acid. In one case, one water would be the base. So in this case, this is going to be our acid as it's losing its H plus. This is going to be our base as it's picking up its H plus, which again means the base here, this would be our conjugate acid. While this acid over here would be our conjugate base. And this is what is sometimes referred to as the autoionization of water. This is essentially what's happening with water. And this is why when we talk about sort of the strongest acids and bases that can exist, in water, that's why we often refer to as H plus and OH minus as those guys, as sort of the really strongest representation of an acid and base that can exist in a water solution. All right, so why don't you take a second here and try to figure out which of the following are conjugate acid-base pairs. So which of these would classify as a conjugate acid-base pair? So take a minute or so here and go through them and see which ones you think are pairs with each other. Remember, what you're looking for is only a difference of 1 H plus. Okay, so let's take a look. So again, the big deal is really H plus, and what we're looking for is just a difference of 1 H plus. So when we look between these two guys here, there definitely is a difference of 1 H plus, but the problem is there's also a difference of an oxygen. There's an oxygen in one, not in the other, so this cannot be a pair. When we look at these two here, there is a difference of an H plus, but that's not the only difference. It's actually 2 H pluses. And again, in order for them to be pairs, the only difference that you could have is 1 H plus, and that means that this guy cannot be a pair either. NH4 plus, NH3, again, the difference here is actually only 1 H plus. And that means that this guy actually is a pair. Again, you can see it whichever way you want. You can put an H plus on the NH3, you get NH4 plus, or you could subtract the H plus off. Number 4 here, H3O plus and OH minus, not a pair. Again, the difference here is actually 2 H pluses, and that's too many. And obviously, none of the above would not be the right answer. So it looks like out of all these, number 3 is the only conjugate acid-base pair that we see there. Any questions on that particular one? Now, you may be asking, so I want to get your question. So 1 is not a pair because these are the two things we're dealing with, HCl and OCl minus. So the difference is 1 H plus, right? But there's also an oxygen here and not here. So that's why they're not related to each other. So again, the only difference is 1 H plus. Now, some may be asking, why are these guys not pairs? And we'll talk a little bit more about this a little later, but just to sort of tie it into what we're talking about now, H2SO4 is sulfuric acid, and sulfuric acid is what is known as a diprotic acid, and it has 2 hydrogens that can come off. But hydrogens or H pluses, they come off not all at once. They actually only come off one at a time. So acids will lose hydrogens or H pluses one at a time. So the first thing that will happen is the H2SO4 will lose that H plus and make HSO4 minus. Then what will happen is the HSO4 minus will lose that H plus and make SO4 2 minus. does not like what I'm drawing here. Jeez. Sorry about that. I got all those extra lines. It's still drawing. All right, let's try that again here. Let's erase some of my wild lines here to see if we can get rid of some of this. There you go. And maybe get rid of that. There you go. Got to clean it up a little. There we go. And almost. All right. All right, let's see if we can put it back together. Maybe. There we go. So, whoops, and I guess plus an S over here. There we go. All right. And while we're erasing here, sorry, a little slide cleanup here. There we go. Let's try this again. All right, let's see if this will be any better here. There we go. All right, now that we don't have 400 lines through it, let's take a look. So what's going to happen here, again, is like I said, the very first thing that's going to happen is the first H plus will come off of the sulfuric acid and make HSO4 minus. Then that HSO4 minus will lose the second H plus and make sulfate. And what we see here is actually it's a stepwise process that occurs. And it is much easier, as we'll talk about, to remove the first H plus than the second. When you remove the first H plus, you know, you're removing it from something that's neutral. When you remove that first H plus, then you have something that is negatively charged, and you're trying to extract something that's positively charged. So it's much harder to remove actually the second H plus in this case. But in terms of relationships, this guy here, our original, and this guy, they are partners with each other. The only difference between those is one H plus. And our guy here and our sulfate are actually partners with each other as well. Again, the only difference is one H plus. But we cannot jump directly from our original to the end, as the difference is more than one H plus. The difference obviously is two H pluses in that case. And sometimes we think about it losing both hydrogens all at once because we oftentimes will look at just the overall reaction that's there. And if we add that overall reaction together, what we get is our H2SO4 going to our two H pluses and our sulfate. And again, this will cancel and this will cancel as well. All these extra lines, it does not like to slide apparently. But again, it's a stepwise fashion and those two are related to each other. Any questions on that? So why don't you try this one here? We have C6H5NH2. What is the formula of the conjugate acid? So remember that when you are given a formula and you're asked to calculate the conjugate acid of it or even the conjugate base, sometimes it's helpful to think backwards, although in this problem they kind of tell you what it is. The relationship, as we saw, is we have an acid and a base, and we have a conjugate acid and a conjugate base. And what this means is the relationship is if we have an acid on this side, it is related to the conjugate base on that side. And if we have a base on this side, it's related to the conjugate acid. So if we were asked to write the conjugate acid like we are in this particular problem, we want to think backwards about it. And what we would think about it backwards is what we are dealing with is a base. And that means that the definition of a base is a proton acceptor, which means we need to put the H plus on. So really you should know that obviously you either going to take the H plus off or put it on. So in this case, we would just put it on. So we would just go C6, H5, NH3 plus, which looks like number 2 here would be our answer in that particular case. So sometimes they won't always, like in this problem, tell you, hey, it's a base or hey, it's an acid. They'll just ask you to write the conjugate acid or the conjugate base, and you need to sort of know what that is. So for example, if we had HCO3 minus, why don't you write the conjugate acid for it? And why don't you write the conjugate base for it? So take a second and write down both of those. So make sure you get the right answer. Okay, so let's see how we're doing. So again, obviously, as we talked about, you're either going to put the H plus on or take it off. So in this particular case, if we go this way and we want the conjugate base, looking at our relationship, our conjugate base is over here. That means in this particular case, the HCO3 minus would act as an acid, and that means it will donate its H plus, which means the conjugate base is CO3 2 minus. While if we go the other way with our conjugate acid, just like in this particular problem here, if we're looking for the conjugate acid, that means the HCO3 minus will act as a base and it will accept an H plus, which means its partner would be H2CO3. Now, as you can see in this particular case, the HCO3 minus can in one case act as an acid, and in another case act as a base. So things that have the ability to act as either an acid or a base are what are known as amphoteric. Amphoteric substances are substances that can act as either an acid or a base. And a lot of times you come across those with something with a hydrogen, like what we see here with bicarbonate, and a negative charge. It has the ability to kind of go both ways. Water can do that as well. As we saw previously, one water was the acid, one water was the base. So it also has the ability to basically act as an acid or a base. And again, that is what's known as being amphoteric. Any questions on conjugate acids or conjugate bases? Obviously, you need to be able to write the formulas for the conjugate acid and bases, identify things as conjugate acid bases and pairs. Any questions on any of that there? So then let's talk about water and the ion product of water. Water can react with itself and set up an equilibrium. And just like we talked about with our equilibrium constants, we can write a Kc for it. And just like what we were talking about, we would not include water, right, as it is a constant. And that gives us a relationship that's known as Kw. And Kw is the ion product of water. And Kw, for the most part, is a constant value, which is what's in this box here. The concentration, and that's what these little brackets mean, right? That is concentration, and that's usually the molarity we're talking about. The concentration of H plus times the concentration of OH minus will give you 1 times 10 to the minus 14. And again, that's what's known as Kw. And we could use Kw to calculate the H plus concentration in a solution. That essentially is the acid part of the solution. We could also use Kw to calculate the OH minus concentration, which is essentially the base part of the solution. It's really the same calculation regardless of which one you're given. You basically will take whichever one you're looking for. So for example, if you want the H plus, that would equal 1 times 10 to the minus 14 divided by our OH minus. Or vice versa, if you had the OH minus you're looking to solve for, 1 times 10 to the minus 14 divided by the H plus concentration. Just a side note here as we get into this chapter for sure, and future chapters as well, you definitely, I'll say it one more time, definitely, yeah, you want to make sure that you do use your exponent button, yes? So make sure that you are using your exponent button on your calculator. And depending on what calculator you got, I think we might have talked about this earlier, but just in case we didn't, most calculators have the 2 buttons on the left, one of those 2. And that EE button or the EXP button stands for the times 10 part of the number. So you should hit that and not hit anything like the multiplication, the inverse log, or anything like that. So if you're putting exponents into your calculator, doing those type of things like shift log or carets and multiplication buttons, you're going to find yourself off in all these calculations. So make sure that you do use your exponent button. If you actually have an exponent button that looks like the one on the right of the screen, I'm sorry, but no, I'm just kidding. Kind of the newer calculators will sometimes have a button that actually does look like on the right. And unfortunately, in most of those calculators, they're programmed kind of weird, which means if you do not put parentheses around every single number that's in scientific notation that you put in that calculator, it will do the math wrong. So you could use it, obviously, and you should use it. But if you do have that sort of button instead of the EE button or the EXP button, you do have to be a lot more careful on how you punch it into your calculator. And again, if you don't put parentheses in the right sort of spots around every number, you will find yourself off in terms of your answer. The good news is if you got the EE button or the EXP button, you could pretty much be sloppy as to how you put it into the calculator. Usually it'll come out okay. You don't have to worry about parentheses or anything like that. But again, if you sort of have that button on the right there, and some of the newer ones do have that button, you do have to be really careful how you punch it in. So definitely make sure that you are using your exponent button. It's really important. Otherwise, again, you'll find yourself off. The way you can recognize that is usually the front part of the number is all good, but that exponent part is like just off. It's like you have to the minus 36 instead of like the minus 35, and that's usually an indication that you're not punching it in correctly. But back to Kw here, we can use it, like I said there, to solve for either the H plus or the OH minus concentration. And depending on what you get there as to what type of solution you would have, if the H plus concentration equals the OH minus concentration, and by the way, that would mean that they both equal 1 times 10 to the minus 7, that would be a neutral solution at that point. If you calculate the H plus concentration is larger than the OH minus concentration, so essentially the acid part is larger than the base part, then it's an acidic solution. And if you calculate the OH minus concentration is larger than the H plus concentration, then it would be basic. There is a relationship between H plus and OH minus, and H plus as one goes up. So as the OH minus, as the H plus goes up, the OH minus concentration goes down, and vice versa. As the H plus concentration goes down, the OH minus concentration goes up. So they do run opposites of each other. Again, one goes up, one comes down. And again, that's an important relationship to keep in mind. So let's try our calculators, make sure everything works out okay. What is the concentration of OH minus in an HCl solution who has an H plus concentration of 1.3? So take a moment here and see what you come up with. Make sure your calculators all work. I'll grab a calculator, see what's going on. Okay, so we're obviously going to be dealing with Kw here, which is our H plus and our OH minus, equals 1 times 10 to the minus 14. In this case, we're given the H plus, so we're looking for the OH minus, and that would be 1 times 10 to the minus 14 divided by, whoops, a little far on that, our 1.3, and that will get us, looks like 7.7 times 10 to the minus 15. And this would be molar, as we are looking for a concentration here. Any questions on that calculation there? Now, if we wanted to know, is this acidic, basic, or neutral, we would compare our H plus concentration to our OH minus concentration, and we see that the H plus concentration is larger than the OH minus concentration, and that means it's going to be acidic. I apologize by the extra lines here coming out today. Any questions on that? Okay. I think we got another one here. So why don't you calculate this one? What is the OH minus concentration? And again, is it acidic, basic, or neutral? All right, so pretty much same calculation here. We're going to take our OH minus is equal to 1 times 10 to the minus 14. We're going to divide it by 1.2 times 10 to the minus 6. Again, we want to make sure that we do use our exponent button here. And if we punch that in, it looks like we end up with 8.3 times 10 to the minus 9 molar for our OH minus. On your calculator, you might have ran out of room and it might just have a bunch of zeros with an 8 at the end. But if you put it into scientific notation, that's where the 8.3 comes from. My calculator did the same thing. It went all the way to the end with an 8. But then when I converted it to scientific notation, it gave me that extra digit. Now, what we want to do is compare the concentration of H plus to the concentration of OH minus. And hopefully when you do that, you will see that it is the H plus concentration that is larger. So this would be acidic in this case. So it is going to be an acidic solution. Again, because the 10 to the minus 6 is a larger number than 10 to the minus 9. A reminder that when you have a negative exponent, the smaller number is actually the larger number, because 10 to the minus 6 means that you're going 6 places to the left with some zeros. 10 to the minus 9 means you're going 9 places to the left with a bunch of zeros. So let me answer your 2 questions here. For the most part, and as we talked about with the equilibrium constant, the Kw is an equilibrium constant. And unless otherwise noted in a problem, you could probably assume that it is at 25 degrees Celsius, and it's probably pretty safe to use the 1 times 10 to minus 14. Now, if you have a problem where they specifically said, hey, it's at 22 degrees Celsius, they most likely will either give you a table with the Kw or give you the Kw value at that temperature. But otherwise, probably 99.9% of the time, even if they don't mention temperature, you could probably safely use the 1 times 10 to minus 14. It's almost assumed that it's 25 degrees Celsius. And if it's not, like I said, they will definitely tell you it's not 25 degrees Celsius. And you would be correct. You would want to find the K value for you would want to find the K value for it at the Kw value for it at that temperature. Yeah, so how I got the extra decimal to put here. So before I'm going to go back and look at my calculator here. I didn't have my calculator originally in scientific notation. So originally on my calculator, for example, the answer came out like 0 point. Oops, 0 point. And we have like 8 zeros. 1, 2, 3, 4, 5, 6, 7, 8, and then 8, something like that, I think, right? 1, 2, 3, 4, 6, 7, 8, 9. So that's originally what I got on my calculator when I did it. I put my calculator into scientific notation, and then that's how I got to the 8.3. So again, your calculator may not be right now in scientific notation mode. If it's not, then you probably got a number like I just wrote on the screen there, where it probably just runs out of room and kind of just rounds that last number to 8 and leaves it there. So, and it's hard to tell you on your calculator how to get it there, but you could usually on most calculators convert it so that all your answers come in scientific notation if you want that to happen. And that's how I got the extra digit there. Other questions on that? So there's that. So then let's talk about pH, and pH is a measure of acidity. And just rearrange some stuff here so I can actually see the screen. That'll be good. All right. So we use the pH, and the pH scale does run from 0 to 7 to 14. So when we talk about the pH scale, goes from 0 to 7 to 14. Below 7 to 0 is acidic. Above 7 to 14 is basic. And technically speaking, dead on 7 there is neutral. And as you go from 7 towards 0, it becomes more acidic. As you go from 7 to 14, it becomes more basic. And technically speaking, 7 is neutral because at 7, the H plus concentration equals 1 times 10 to the minus 7, which gives you a pH of exactly 7. So technically speaking, 7 is dead on neutral. And when we calculate pH, that's the formula. The pH is equal to minus the log of the H plus concentration. Now, when we are measuring this, this is basically a measure of the free H plus that's floating around that solution. So it's the free H plus ions floating around in that aqueous solution is what we're measuring here. Now, if you have a display calculator, you type that formula in exactly the way you see it. So that means you hit the negative button, not the subtract button, the log button, and you put your concentration in using your exponent button. If you have a non-display calculator, you have to go backwards in this formula when you punch it in, and every other formula we're going to talk about here in this chapter. You would start with the number, punch it in scientific notation. You then would hit the log and then hit the negative button. If you're not sure what type of calculator you have, you could just hit log. If it says log, congratulations, you have a display calculator. If you hit log, it says error. Congratulations, you have a non-display calculator. So that's the way you could kind of check it. So display calculators, this one and every other one, you just write it exactly the way it's written, punch it in. If you have a non-display, you got to go backwards in this formula and all of them. So you start with the number and work your way backwards. Now, we measure pH, and it could tell us if the solution is neutral, basic, or acidic by the pH value that we get. And you always want to look at pH when you're trying to determine if it's acidic, basic, or neutral. It is always the pH scale that you want to look at, and that's what you want to try to determine. So as I mentioned before, technically neutral is a pH of 7 because at that point, the H plus concentration is 1 times 10 to the minus 7, which if you put it into your pH equation, will get you a pH of exactly 7. If it's acidic, it's going to be less than 7 in terms of the pH. And that is, as we've been talking about, the H plus concentration is greater than the OH minus concentration and is greater than 1 times 10 to the minus 7. And H plus concentration is less than the OH minus concentration. It will be basic, and that will lead you to a higher pH above 7. The pH goes up as the H plus concentration goes down, and obviously vice versa. If the H plus concentration goes up, the pH goes down. And again, that's an important relationship along with what we saw earlier, that the H plus and OH minus are opposites of each other. So again, if one goes up, one goes down, one goes down, one goes up. So they are, again, related to each other. All these things, that's really important. So let's talk about everybody's favorite thing, which is significant figures and pH. When we calculate something like pH, the pH should have the same number of decimal places as the number of significant figures in the concentration value. So if you calculate the pH or a value like pH, you should look at the concentration value, and the number of significant figures in the concentration value is how many decimal places you should take the pH to. So let's just try one to make sure our calculators work. Let's say we had an H plus concentration of 1.2 times 10 to the minus 4 molar. What is the pH? So give it a calculation and calculate it to the correct number of decimal places. And I will do it too because I just made up that number. All right, so let's first start with the actual pH part of it. So to calculate the pH, we would put it into pH is equal to minus the log of 1.2 times 10 to the minus 4. Again, if you have a display calculator, you hit the negative, you hit the log, you hit 1.2, your exponent button, and negative 4. If you have a non-display calculator, you go 1.2, exponent button, negative button, 4, log, and then make it positive. And if you punch that in, you will get a number on your calculator, perhaps like 3.920818754. And obviously, that is too many digits, but most importantly, let's start with, hopefully everybody got at least that number to show up, hopefully. Now, when we're talking about what is the proper answer you should give, The proper answer here is 3.92 is the proper way to display that. So when we look at the concentration, it has two significant figures. That means we do not end up with two significant figures in our pH. We end up with two decimal places in our pH. So two decimal places in our pH, which would take us to 3.92. This, by the way, would be an acidic solution as the pH is less than 7. Also, while you're asked that question, is it acidic, basic, or neutral? By the way, there is only one answer to that. It's either acidic, basic, or neutral. Not all three, although I don't know if I've given all three before, but I have seen people answer the same solution as both acidic and basic at the same time, but it should only be one. Yeah, so again, when we talk about sort of significant figures, when you calculate something like pH, what we're looking at is the actual concentration value. So in our case here, that's the 1.2 times 10 to the minus 4. That 1.2 times 10 to the minus 4 has two significant figures, which means when you calculate the pH, you're not looking for significant figures in the pH value, but what that will tell you is how many decimal places you should go to. So decimal places should be 2 to match the sig figs. And that's why we go to 3.92, which is 2 decimal places. So when we're doing a calculation like pH, we're going from significant figures in the concentration to decimal places in the answer. And if we go the opposite way, which we'll talk about as well, we are going from decimal places to significant figures in the concentration. So it works both ways, depending on which way you're going. But again, we're going sig figs to decimal places, not sig figs to sig figs. Other questions? Okay. Now, there is a similar scale to pH, and that is one that actually measures the pOH, and the pOH measures the OH minus concentration. So the name kind of tells you pH means you need the H plus concentration. pOH means you need the OH minus concentration. And the pOH here, as you can see, is minus the log of the OH minus concentration. And the nice thing about that is there's a nice relationship between pH and pOH. And if you add them together, that's going to give you 14. So if you take the pH plus the pOH, you will get 14. And that sometimes will allow you to kind of do the calculation a little bit easier without having to use kW. You can still use kW if you want, but you can kind of sometimes calculate these things without using kW. Now, the pOH scale is not the scale that you should use to determine whether or not a solution is acidic, basic, or neutral, because most people in their head have the pH scale, not the pOH scale. The pOH scale runs opposite of the pH scale, which means on the pH scale, as we can see in this picture, goes from 0 to 7 to 14, and 0 to 7 is acidic, 7 to 14 is basic. If you run the pOH scale, which runs the same, 0 to 7 is basic, above 7 to 14 is acidic. So they actually run opposites of each other. So this is definitely the place where people end up giving this two answers for the same question. So that question, like I was saying earlier, where it should only be acidic, basic, or neutral, what will happen a lot of times, people will calculate the pH and then calculate the pOH and go, oh, the pH is less than 7, so it's acidic. And for the same solution, they'll go, oh, the pOH is above 7, so it's basic as well. So they'll give both answers and stuff like that. So I would recommend highly to look only at the pH scale, because that's usually what we have in our head. And obviously, this should only be one answer. A couple of other important things on this slide, as we see, this is a pH meter. pH meters we use, obviously, to calculate the pH or figure out the pH of a solution. Basically, an electrode like you see here in the beaker. You put it in, and again, it measures the free H plus concentration in the solution. One of the earliest ones was made by Beckman there. and you can just pop it in and basically get a digital reading of the pH. Some other sort of things that are important in terms of calculation is if you have the pH given to you, you could actually calculate the H plus concentration by taking the inverse log of the minus pH. So if you're given the pH and want the H plus concentration, you do the inverse log. When you type that on your calculator, most of the time that's a 10 and a caret in the pH, or how a lot of people do scientific notation on their calculator. So inverse log on most calculators, top left corner is your shift button, your second button, and your log button. To do that is usually how you get that caret going in there, that 10 and a caret, and then negative pH. You also can do the same calculation for POH. If you have the POH, you can get the OH minus concentration. Exact same calculation, the inverse log of the minus POH, which again on your calculator, a 10 and a caret minus POH is typically what you put up there. So those are some 5 important formulas in terms of calculating pH and stuff like that, or POH or H plus and stuff like any of those sort of values. So you can obviously calculate any of those things, and there's a couple different ways you could do it. They all should get you to the same sort of location, maybe with some rounding slightly different, but you should end up pretty close to the same. Yeah, in terms of exams, you are required to know formulas, any type of constants or table type values would be provided to you, but something like pH is equal to minus the log of H plus would not be provided for you. POH you need to know, so you do need to know formulas, but again, anything that's a constant value would be provided to you. So something like 1 times 10 to minus 14 would be provided to you as well. Any other questions on that? Okay. So let's do some of these calculations here and see what we end up with. So here's a couple. So take a couple of minutes here and work through these. We got the rainwater. pH is 4.82. What is the H plus concentration? And on the bottom there, the OH minus is 2.5. And what is the pH? So take a couple of minutes here and figure that out. Okay, so let's take a look and see. In this first one, we're given the pH and we're looking for the H plus concentration. So again, if you are given the pH, that's going to allow you to get to the H plus by taking the inverse log of the minus pH. Again, on your calculator, when you punch that in, usually will pop that 10 and a caret up. And again, you want to make sure you make it negative, not your subtract button, 4.82. And if you do that, all that good stuff there, it looks like you will end up with 1.5 times 10 to the minus 5 molar in terms of the concentration. So as we went backwards in this case, as we went from pH to, get rid of that line maybe. Oops. As we went from pH to our concentration, we followed the same rules in terms of significant figures. So our original number had 2 decimal places. So our concentration has 2 significant figures. So going backwards. Any questions on that particular one? By the way, this obviously should be acidic as it is less than 7. Looking at the second one, the OH minus concentration is 2.5 times 10 to the something. I got things on my screen. Let me see what that says. Minus 7 looks like. To the minus 7. What is the pH of the blood? In this particular case, since we have OH minus given to us, we could actually calculate the POH first. So the POH in this case equals minus the log of our 2.5 times 10 to the minus 7. And we take minus the log 2.5 to the minus 7, gives us 6.60. And again, this is not our pH, but this is our POH. So then we could use the relationship that the pH plus the POH equals 14. That means that the pH would equal 14 minus our 6.60. And if we do that, looks like a 740 on our pH. Any questions on that calculation there? Now, 7.4 would technically be slightly basic, just over 7 there. So again, for our class, so there's no misunderstanding, we'll go with 7 on the nose as neutral. Anything above 7 will be slightly basic. Anything less than 7 will be slightly acidic, unless it's like 7.0 something, then you could call it obviously neutral. But we'll just keep it like that to make it easy, hopefully, or very simple. It's got to be 7 on the nose there for it to be neutral. Any questions on any of those calculations? Obviously, you could have on the bottom one there used KW and got the H plus concentration and then went into the pH equation. Again, should give you pretty much the same answer. All right, so why don't you do this one? pH, POH, and OH minus. If we have H plus, 3.5 times 10 to the minus 6. All right, so here we have the H plus concentration. We're looking for everything else. So because we were given the H plus concentration, we can go right into our pH and calculate that. Minus the log 3.5 times 10 to the minus 6. And that will get us 5.46 as our pH. Again, 2 sig figs and 2 decimal places there. Because we have the pH now, we can get the POH is equal to 14 minus the pH. Again, from that pH plus POH equals 14 relationship. And that would get us, we subtract 14, 8.54 as our POH. And lastly, we want the OH minus concentration, which we really have 2 ways we could get that. We could use KW in the original value to get the OH minus. We also could take the POH now that we have and take the inverse log of the minus POH. So again, that's going to be a 10 and a caret on your calculator, 8.54, making a negative. And that would get you, looks like 2.86 to the minus 9. And this solution would be acidic, yeah. Again, the pH is 5.46. You do not, like I said before, want to give both answers that it's acidic and basic at the same time. Any questions on how to calculate any of those parts there? Obviously, you need to be able to calculate the pH, the POH, the H plus, the OH minus, and determine if it's acidic, basic, or neutral. Any questions on any of that there? All right, so let's talk a little bit about strong acids and weak acids and sort of the relationships that we see here. Oops, good talk. So a strong electrolyte, as you may remember, if something is a strong electrolyte, what that essentially means is when it goes for a swim in water, for example, it will 100% break apart into its ions. You will have none of the whole units together. So something like sodium chloride and most salts, when they're in an aqueous environment, they are strong electrolytes, which means when we have something like sodium chloride in a solution, you no longer have any of the NaCl units together, but it's 100% sodium ions floating around and 100% chloride ions floating around. So I think the answer is yes. So just to go back, I think there's a question on the answer there. So just to make sure, I wrote it right there. I didn't mess anything up. Oops, there it is. Come back. So you are correct. I did write it wrong there. My bad. Sorry about that. This is 2 significant. This is 2 decimal places. So you are correct. This should be 2.9 times 10 to the minus 9. Thank you. It should definitely be that. There you go. And again, that would be based off of the 2 decimal places in the 8.54. It should give us 2 significant figures in there. Thank you. That should be correct. See, we all make mistakes. That's why they invented erasers, right? All that good stuff, right? All right. So coming back here to our strong electrolytes. So strong acids and strong bases are also strong electrolytes, which means when they are in solution, they will 100% break apart into ions. And just some examples of some strong acids is what we see down here. HCl is a strong acid. So again, when it breaks apart, 100% of it breaks apart into ions. So in solution, 100% is what you have on this side. And these are all strong acids, which means for each of these reactions down here, as we talked about earlier, you could write each of them just like this. To represent the exact same thing. And again, that's where we would have our H plus versus our H3O plus. But again, we would have 100% of these ions in there. You would have no HCl units still together. 100% would have broken apart. So hydrochloric acid, nitric acid, perchloric acid, and I think that's sulfuric acid there. Those are all strong acids. They all 100% in solution are on this side. None of these guys are still together over here. And that's why they're really strong acids, because when these guys go for a swim in the solution, they produce a lot of free H plus. And that's sort of your definition of an acid, is the ability to produce H plus. So all they pretty much need to do is go into the solution. They will generate a lot of H plus really fast and will produce a lot of that and make it a strong acid. Some other strong acids, HBr is a strong acid. HI is a strong acid as well. So those are also some strong acids. Hydrobromic acid, hydriodic acid, they're actually really strong acids as well. Now, on the other hand, we do have weak electrolytes, and weak electrolytes, when they go for a swim or when they're in a solution, they actually mainly stay together. So they mainly stay together. So this is acetic acid. When it goes into solution, it will break apart into acetate and H plus. But in solution, it will only produce a few of these guys. But again, mainly stay together. But because it's still able to produce a few ions, like a few H pluses, it's still considered an acid because it has that ability to produce that H plus. But it's not going to produce anywhere near what you see in a strong acid. Again, strong acid, 100% going to break apart a lot of H plus really quickly. But in a weak acid, you're going to produce just a little bit of H plus, not as much, but still able to produce H plus, which is why it's still considered an acid. The other major sort of difference between sort of a strong electrolyte and a weak electrolyte is usually the arrows that you see. In a strong electrolyte, it is a one-way arrow, one-way street. Everybody's going to the product side to break apart into ions. In a weak electrolyte or a weak acid or weak base, it is, again, that reversible reaction where it's going forward and reverse, but mainly staying on the reactant side still together. Here are some weak acids: hydrofluoric acid, nitrous acid, and water as well. And again, we can see in each of these, we have our arrows heading in both directions, which is a big indication that it's a weak acid. And just like the strong acid, you can write this same reaction for HF this way as well. So again, they're both the same, no matter how you want to write it. And like I said, in problems, I probably will write it just like that. But each of these are able to produce H plus, but really nowhere to the extent, again, of a strong acid, but they still are able to do that. So still considered an acid in that case. Our strong bases here are, again, strong electrolytes, which means just like our acids that are strong acids, 100% of what you got in that solution is what's on the product side. None of the sodium hydroxide will still be together. And what that means is it produces a lot of free OH minus. And again, since that is a relationship between OH minus, as we make a lot of OH minus, the amount of H plus will go significantly down. And that means the pH will go up, obviously. And because it produces a lot of that hydroxide, we will see a relatively high pH above 7 in our bases or strong bases. As you can see here, a lot of strong bases come from group 1 and group 2 on the periodic table and have hydroxide OH in it as well. So again, as we talked about at the beginning, alkali metals, alkaline earth metals. Alkaline means basic, so a lot of our strong bases do come from group 1 and group 2 on the periodic table that has hydroxide actually in the formula. There are also weak bases as well, which, just like our weak acids, will have those arrows heading in both directions. So when we have our weak bases, again, mainly this is what we got going on this side. We'll produce a little of these guys. But again, because it's able to produce at least a little of free hydroxide, it does meet the definition of a base. And usually our weak bases do not have OH in the actual formula. They're able, though, to react with water and produce hydroxide, which is like what we see in both of these reactions, which is what makes them, again, a base. Now, the relationship between a conjugate base and a strong acid has no measurable strength. So the relationship between things, which is really important for later on this chapter, is if it comes from a strong acid, our base is conjugate partner. Is conjugate base or conjugate acid will be relatively weak. So if a partner, a conjugate acid or base, comes from a strong acid or base, is partner, the conjugate part of it, will be relatively weak. And vice versa, if we have a weak acid, our base, the conjugate base and conjugate acid will be relatively strong. So it's sort of an opposite relationship. If something comes from a strong acid or strong base, it's relatively weak. If it comes from a weak acid or a weak base, it's relatively strong. What does that mean? We're going to talk about later in this chapter, but basically what that means is if something comes from a weak acid or a weak base, it has the ability to continue to react in that solution. And typically what it will react with is water. So it has the ability to continue to react with water and continue on and have an effect on the pH, which we'll talk about. That's essentially what hydrolysis problems are. H3O plus, as I mentioned, is sort of the strongest acid that can exist in a solution, while OH minus is sort of the strongest base that can exist in a solution. Any questions on that? Here's just a table, not from your book, but you have a similar one, again, showing you some of the strong acids and some of the weak acids, and obviously our strong bases on the opposite side. So strong acids on the left going to the top, weak bases, conjugate bases on the top, on the right going down. You don't really need to memorize this table. I would say you would need to, I think at this point, you should be familiar probably with what is sort of considered a strong acid. There'll definitely be a lot of information to help you determine that if you're not 100% sure. But I guess would say, we saw these on an earlier slide as well. You should be familiar that, you know, these guys here, at least these, whatever we got there, or 6 at least. These 6 are pretty much strong acids. They're the very common ones that you come across a lot. So I would say out of everything on this table, you should at least kind of know the strong acids, because that's probably important. But again, there'll be a lot of information as we go through these problems that will help you kind of decide that. Other questions? Okay. So it looks like probably a good stopping place, I think. So we'll stop here for lecture. We ran a little bit over, so I tell you what, we'll start about about 5 after 3 or so. There, get a chance to stretch your legs and all that good stuff. Actually, we'll start 3:10. Get a good chance to stretch your legs, stand up, walk around for a little bit, and we'll start lab at 3:10. Come through the lab, obviously meeting. We're doing experiment number 4, which is Le Chatelier's principle. So we talked about that last time. So we'll kind of do it the same way we've been doing it. We'll kind of do some stuff together, or watch the video together, and then obviously you could finish it up and all that good stuff. Any questions on anything before we stop lecture here? Okay, again, if you didn't type here into the chat, make sure you do that for roll, and I'll see everybody in about 3:10, so about 15 minutes. We'll start the lab, come through the lab meeting, okay?